In this section of notes, we're going to expand on what we learned in the previous section about conditional probabilities and also talk about a new visual. So we looked at these formulas before. These were kind of our formulas for conditional probabilities. So find the probability that event A happens given that event B has already happened. If we were to take this formula and solve it for A and B, so solve it for the numerator of the fraction, we would accomplish that by multiplying both sides by the denominator, or multiplying both sides by probability of event B. That would leave us with this formula here. So this is actually called our general multiplication rule. And this iteration of the formula is not on our formula sheet. The one that's on our formula sheet is the one that I just showed you where it's written as the fraction, but you can easily multiply both sides by the denominator and come up with this formula. This is the formula you're going to use anytime you're doing an and problem. So find the probability that this happens and this happens, or event A happens and then event B happens. Anytime you have a question like that, this is the formula you're going to use. So if we want to find the probability that event A happened and then event B happened, we find the probability that event A happened and then multiply it by the probability that B happens given that A has already occurred. So for example, let's say I wanted to flip a coin twice and I wanted to find the probability that I got 2 heads. So each of the branches in this tree diagram represents an outcome. So when I first toss a coin, it can either be a heads or a tails, and the chance of it being a heads is 1/2, the chance of it being a tails is 1/2. If I know that the first flip was a heads, then the second flip can either be a heads or a tails. 1 out of 2 is the chance of each of those happening. Same thing if I got a tails first. My second flip can either be a heads or a tails, and the probability of those happening is 1 out of 2. So the probability that I get 2 heads, that's this route through my tree diagram. So I got a probability of 1/2 of getting the heads on the first flip, probability of 1/2 getting it on the second flip, probability of getting a heads on the first one, and then getting a heads on the second one. So I multiply those and I get my final answer of 1/4. Now, whether or not a coin ends up being heads on a second flip shouldn't matter whether or not it was heads or tails on the first flip. So that's an example where we're looking at things that are independent. Here we're going to look at another example. So these events are dependent. So here we want to find the probability that teens are online and have a posted profile. So we know that 93% of teens have internet access and 55% of them have some sort of posted profile. So we want to find the probability that they have both. This is where a tree diagram really comes in handy. So the 93% is showing up here. So the probability that they're online. Now they didn't give us in the problem, but we could figure this out. If 93% of teens have internet access, that means the rest, or 7%, because it's got to add up to 100, they don't have internet access. And then similarly, if 55% of the teens that are on the internet, if they have an online profile, that's this 55%. And then the rest, so subtract from 100, that gives us this 45%. For the other branches, if they're not online, they can't have an online profile, so there'd be a 0% chance of that happening, and a 100% chance that they don't have an online profile if they're not online. So that's how we're coming up with all of these little branch values. So if I want to answer this final question of what percent of teens are online and have a posted profile, that means I have to find the probability that they're online, and then I need to multiply, and means multiply, the probability that they have a profile given that they're online. So I'm taking these two values in this branch and multiplying them together. Now we talked about independent events before, where we said that if the probability that one event happens doesn't impact another. And we had this formula in our previous section of notes. Now, if the two events are independent, that means the probability that one happens doesn't impact another. I can kind of simplify this formula, and I can just multiply these two things together. So the probability of event A happening times the probability of event B happening. So where that's going to come in handy is something like this. So again, this will only work when events are independent. So I've got these O-rings, and they work, they function properly 97.7% of the time. And I want to find what's the probability that I pick 6 of these O-rings and all of them are working properly. So that means the first one works, the second one works, the third one works, the fourth one works, the fifth one works, and the sixth one works. They all work. Since this is an and problem, I'm going to be multiplying. And since they are, the probability that they do function properly is 97.7%, they're all going to be that value. Now I could shorten this by writing 0.977 to the 6th power. That would save a little bit of writing. So there's an 87% chance that I picked 6 of these O-rings and they all work appropriately. Now if there's an 87% chance that they all work appropriately and the shuttle launch is successful, then if I subtract that from 100%, then that means there's a 13% chance that it wouldn't work. Now that means there's a 13% chance that at least one of those O-rings would fail. So that's kind of a trick for you here. If you ever have a problem that's worded that way, what's the probability that at least one O-ring fails? Then you're going to do 1 minus the probability that none of them fail. So that's essentially what we found up here. The probability that none of the O-rings fail is 87%. The probability that at least one fails is 13%. So anytime you see at least one, that's the same thing as 1 minus the probability of none